Today we are going to be talking about inverse functions. Before we talk about what an inverse function is, let's talk about an inverse relation. So an inverse relation is a relation that results from exchanging input and output values of a function. So taking your x and y values and swapping them will give you an inverse relation. Now, if that relation that you end up with is a function, then we can call it an inverse function. Now, if we talk about the graphs of inverse relations, let's say you have some function f, and a comma b is a point on the graph of f, then for the inverse, b comma a will be a point on its graph. Another way to think about this is comparing the graph of a function and its inverse. The graph is going to be a reflection of the original graph across the line y equals x. So let's take y equals x squared, for example, and see how this works. So y equals x squared, we're going to take each point on y equals x squared, so we'll call those points a, b, and we'll graph b comma a in order to graph the inverse relation. So here is y equals x squared. We know 0, 0 is a point, 1, 1, negative 1, 1, 2, 4, negative 2, 4, 3, 9, negative 3, 9. That's probably enough points to help us get a good idea. So we know y equals x squared is simply a parabola. Now for the inverse, we're going to take each of those points and swap the values. Now obviously 0, 0 will stay 0, 0. 1, 1 is still 1, 1. But now you take the point negative 1, 1 and swap it becomes 1, negative 1. Take the point 2, 4 and that becomes 4, 2. Negative 2, 4 becomes 4, negative 2. 3, 9 becomes 9, 3. And negative 3, 9 becomes 9, negative 3. So you can see here we have what looks like a sideways parabola, and graphically you can see how this is a reflection along this line y equals x. Now how do you go about algebraically coming up with the equation of the inverse? Let's take a look at example 2. So say you have f of x equals 3x minus 2, and without graphing we want to come up with the equation of the inverse. So what you're going to do is you're going to first start off by writing everything in terms of x and y. So instead of f of x, I'm going to write y. So y equals 3x minus 2. Now since the inverse is simply swapping the input and output, we are going to swap the x and the y. So this is going to be x equals 3y minus 2. Now since we want to get a good idea of what this equation looks like, we can solve for y. So this becomes y equals x plus 2 all over 3. So to write this, because we know x plus 2 over 3 is just the line 1/3 x plus 2/3, we know this is a function, so I can write this using function notation. G of x equals x plus 2 over 3. Let's do another example. We have f of x equals x squared plus 4x. So again, let's start off by writing everything in terms of x and y. So we have y equals x squared plus 4x. And then we are going to switch the x and y. So that means we'll have x equals y squared plus 4y. And then we have to solve for y. Now notice in this case we have y squared and 4y in there. So we actually have a quadratic. So in order for us to solve for y, we are going to have to move everything over to one side and use the quadratic formula. So since we're solving for y, your a value is 1, your b value is 4, and your c value is negative x. So this means that we have y equals negative 4 plus or minus the square root of 16 plus 4x all over 2. And inside that square root, we can actually take out the square root of 4. So we end up with 2 square root of 4 plus x. And then we can divide everything by 2. So now we have negative 2 plus or minus the square root of 4 plus x. Notice how here we haven't changed it to function notation. I didn't say write it as g of x equals negative 2 plus or minus the square root of 4 plus x. And the reason is because, well, is this a function? Well, no, because if you plug in some value of x, you're actually going to end up with 2 different values of y. One is negative 2 plus the square root of 4 plus x. The second one is negative 2 minus the square root of 4 plus x. So we have this term called one-to-one function, and a one-to-one function is one where the inverse is also a function. Now, in terms of algebraically looking at the function itself, we would say that a function f is one-to-one if f of a equals f of b implies that a equals b. That means that no two x values will give you the same y value. So if a function is one-to-one, we would mean that its inverse is also a function. So for example, we graphed y equals x squared. We know that the inverse of y equals x squared is not a function, so we know that y equals x squared is not a one-to-one function. Now the quick way of testing whether or not a function is one-to-one is to use what we call the horizontal line test. It pretty much works the same way as the vertical line test, except instead of a vertical line, you use a horizontal line. So we say a function f is one-to-one if and only if no horizontal line intersects the graph of f more than once. So let's see an example using the horizontal line test. So determine whether the function is one-to-one. We have x cubed minus 3x minus 1. Now by looking at that, it's hard to tell whether or not it's one-to-one. Really what you're checking for is you're checking to see, are there any two x values that give you the same y value? So if you look at the graph, on the other hand, it actually makes it very easy to tell using the horizontal line test. Well, it looks like we can draw a horizontal line in a number of different places where it crosses the function in more than one place. So this graph fails the horizontal line test, which means we can say g is not one-to-one, and so therefore its inverse is not a function. Okay, so just let's go over some terminology that we've used here and recap. So for inverse functions, we can say if the inverse of f is a function, that's equivalent to saying that the function f is a one-to-one function. Those mean the same thing. It's also the same as saying that the graph of f passes the horizontal line test. So if you see a function and it passes the horizontal line test, you know that its inverse is a function, so you can say that f is a one-to-one function. Those are all equivalent statements. Now, if the inverse function exists, and it is in fact a function, where y equals f of x, then you would use this notation with f negative 1, and you would write this. So if y equals f of x, then x is equal to f inverse of y. Now just to note, the f with the negative 1 that looks kind of like an exponent, it's not an exponent, it's a notation thing. So just know that f negative 1 does not mean 1 over f. Okay, so now we are going to combine what we've learned today about inverse functions to what we learned last time with composition of functions. So a one-to-one function f and its inverse function, f with the negative 1, have these properties where if you compose f inverse with f, it will equal x for every x in the domain of f. If you do it the other way, f composed with f inverse of x, it will also equal x for every x in the domain of f inverse. So if you are able to show that both of these are true, then you can say that those two functions are one-to-one and are inverses of each other. Let's do an example of this. So use composition to verify that f and g are inverses of each other. So what we're going to do is we are going to compose f with g and compose g with f and show that in both cases the result is equal to x. So let's start with f composed with g. So I'm going to plug in 1/2 x plus 2, that's g of x, into the function f wherever I see x. So this is going to be 2 times 1/2 x plus 2 minus 4. Distribute the 2 and we end up with x plus 4 and then a minus 4. And you can see the 4 and the minus 4 cancel each other out, and that leaves us with x, which is in fact what we are hoping for. Now, because in this problem it asks you to verify, that's an indication that you know that it should equal x, and it's just a matter of showing the work to get there. Now let's do it the other way, g composed with f of x. So this time we're plugging in f of x, which is 2x minus 4, into our function g of x. So we have 1/2 and then times 2x minus 4 plus 2. Distribute the 1/2, that leaves us with x minus 2 plus 2. The minus 2 and the plus 2 will cancel, and that leaves us with x. And so because we were able to show that this works in both cases, we composed it in both directions, we're able to show that these two must be inverses of each other, and they both must be one-to-one.